Thank you, Florence, for this nice introduction. Great thanks to organizers for inviting me here. And thank you for people here and online for coming here to this talk. So I would like to introduce to those of you who don't know, to those who already know, I apologize, maybe then it will be less fruitful for you because you already know what it is, the notion of statistical data depths, touching methodological questions with applications and also computational questions, which are actually very important for this notion. So this will be more or less what we'll be speaking about. I'll just present what it is, speak about properties. Does it work? Yeah, it does. About properties, then we will look at several generalizations. We look at some computational advances which allow these methods to be today more used than, say, 10 or 20 years ago. And like we finish with one short slide mentioning open questions and challenges in the area. So in August 2024, there were Olympics, Summer Olympics Games in Paris. So I took from there a data set of final of the female modern pentathlon, and we will look, say, at two variables, the swimming time and the laser run time, both measured in minutes. And we will work with it, like use it as our toy data to take a look at something. So what is actually data depth? There are many ways to introduce it. I'll do it in the following way. Given a sample of data, right, because it's data depth, we speak about data, we ask a question about one particular point. For example, this one, which is the sportsman who was representing Egypt in final. What is the representativeness, what is the belongingness of this blue point to this set of red points? Right? And we want to answer this question in an agnostic way without necessarily assuming kind of statistical model. There was a history how it was done. We'll go directly to the definition, right? So what do we do? To answer in advance several questions, what we do, we define a function. A function which will take the point of interest, the point for which we want to answer the question, does it belong to data set? What's its degree of belongingness, of closeness to some center of this data set? With respect to some distribution, and we would like this function, the data depth, to return us a number between 0 and 1, so that if it's 1, this means that we are very sure that this point indeed very well represents the data set. For example, this is the estimator of location of this data. Or if it's 0, this means that this point is indeed somewhere far from this data and does not necessarily belong to it. In principle, if I speak about d function mathematically, it's infinitely many functions, right? So historically, to somehow give meaning to this definition, there was mathematical formalism developed, which would make it, okay, so this, then if function d satisfies certain requirements, which are called postulates in the data depth literature, then we can say that it's a nice function which is practically useful. So, and these requirements are certain invariances. It's translation invariance, but also we would like it to be linear invariance, which is a relatively strong property. We would like it to be vanishing at infinity, meaning that data are here around 0, around 1, right? And if there is a data which goes somewhere infinitely far, it doesn't belong to our data. We also would like it to be to have some to reflect in a way the belongingness to the data, right? To be high where there is a lot of data, and when we start to go further from the data, that this function decreases. Yeah, and usually we put some technical restriction that if we have some upper level set on this data, that all the set belongs. The border of the set also belongs to this set, to the upper level set. So one can speak about this and give maybe several comments that there is no complete agreement, let's just say, in the literature, even on data depths, that this is the right set of postulates which should be taken. And there are also connections to further sets of postulates. For example, if a notion of data depth would satisfy these requirements which I've shown, it would also automatically be true that if we have a distribution which would be symmetric around some center, then the center would also have the maximum value of the depth function, right? We can say that if what we assumed that the depth is decreasing on the rays, which if we move from center of the data set outwards, that the upper level sets would be star-shaped, but we can actually strengthen that, and we can require this notion to keep the data sets always convex to obtain a quasi-concave function, the data depth. Interesting property is the invariance, and we will say more about that, right? Because it actually can be weakened. It might make sense in one cases, might make less sense in other cases. So about that we will say something additionally. But let's look at an example. And this is a historically first notion of data depth, which is the half-space depth. Half-space depth is defined as the probability of a closed half-space with the restriction that this half-space should contain the point for which we compute the depth. Right, and of course we can quickly construct empirical estimator and have something similar. This is a nice depth notion in the sense that it satisfies all the postulates and requirements I mentioned before. It's purely parametric, it's actually robust, it has direct connection to quantiles and to other nice concepts such as densest hemisphere problem, regression depths, supervised learning, maximum feasible subsystem, floating body. Let's take a look how actually it works. So what if we try to present it, right? So we are interested in finding out how representative is the performance of Egypt in the final of the female pentathlon competition of modern pentathlon competition at the Summer Olympics, right? So what we would do then, we would try to search through all possible half spaces with the restriction that they contain this blue point, right? And we'll be calculating how many points actually fall into this subspace, into this half space, right? And it will be 9, so literal 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points will be in this half space. And what we wanted, we want to minimize this portion, right? We want to find a half space which contains as small portion of the dataset as possible, but still keeping within this half space the blue point, right? So we will do several tries. There are infinitely many of them, and one of them will be optimal, and it will be 6, right? So 5 these points and 6 because the blue point also belongs to the dataset. So this will be the depth will be 6 divided by 16. The portion of the data which is contained in the closed half space containing the blue point. If we take another team, France, for example, another person, so what we will have is that we actually, since France is further, it's in positive sense, but it's in a way it's an outlier, right, or closer to outliers, and we will be searching how many points we can cut off by a half space which should contain this blue point. We would actually have only 2, 1 point and the France itself, right? So then the depth of this observation will be 2 divided by 16. So now what we can do, of course, in such small example, we can just compute depths everywhere, right? And that's what I try to present for the same data set. So here is the levels of the depths with their upper level set. I hope you can see it's like 0.05, then 0.1, 0.15, 2, and so on, right? And here everywhere where it's white, it's 0. And here these are the contours, the borders of the upper level sets, right? Just like on another. So this is the half space depth. This is how it works. And what I would like to say here that this is one of the notions, right? So it's one of the notions which exists. There are also other notions, right? Because as you can imagine, so there can be many functions which satisfy these postulates, actually still infinitely many, but historically there are several of them which make sense, so make practical sense and can be used. So next one, so that was one of them, that was the half space depth, or the Tukey depth, also called location depth, because it actually measures the location of points in the space. The next one would be the one based on Stachel-Donoghue outliningness, which will be called projected depth, yes? So what is right, so literally we'll take projected outliningness, it's kind of distance, and we will apply the decreasing monotone transform to make depth out of it, right? So how does it work? The idea of projected outliningness is the following, that an outlier a point is an outlier if it is an outlier on at least one projection on some univariate linear space, right? So a direction. And basically the idea is then to find such a direction and then measure the outlierness. So outlierness can be measured by something like kind of this statistic of wild type statistic, right? Where we will take the point minus some center divided by the dispersion of this point, right? Of the data. So, and now we'll be searching for direction, right? So, for which this measure would be, on which this, in projection, which this measure would be maximum, right? For example, let's take 2 points, green, which is more or less belonging to the data, and red, which is actually far. So it's supposed to have like low measure of this, high measure of this outlierness, and we will be searching, right? So if we take this direction, of course, it's not very characterizing direction because it will not show us that the red point is an outlier, but if we'll be searching a bit more, we'll find the direction on which the distance actually, the outlierness of red point will be pretty high, right? And there will be such one direction for each observation for which we try to calculate the projection depth. So, and then, yeah, as I said, we just apply monotone decreasing transform to this outlierness, and we obtain something which is called the projection depth functions, which is also a very nice one. It satisfies all the postulates. It is additionally to the half space depths continuous, and it is very robust. Its breakdown point of its median, it's 1/2. So basically, you can take almost half of the data, throw them into infinity, and your median will stay somewhere in a reasonable location. Right, and this is the same picture, so that you see the contours of the points, the contours of these depths, and also the contours like in the 3D, so where we have the two dimensions, and here the depth itself. And so this is another notion. So we looked at half space depth, projection depth. Let's look at another one, which is the spatial depth. The spatial depth is a depth which is based on science, the spatial science, right? So sign would be plus minus and say 0, right? So spatial sign will be just a direction, a vector with a direction, but without amplitude. So what happens if, for example, we try to compute the average sign for this point? Well, we'll compute the differences, right? The differences of the point itself minus each of the points of the data. And we'll take the average, right? So this all is normalized. So this is a spatial sign, which means this is a vector of length 1. So these all are vectors basically connecting 2 points, but then all of length 1, but they're all vectors, right? And now we take the average. But since they're all of length 1 and they look in different directions, the average will actually be vector of very small lengths, right? And then, of course, the lengths will characterize the point that for which we want to compute the depths, and we'll just apply a transform to have it as a depth, and it will be something small, something big, because it will be 1 minus something very small. If we take another point, right, if you want to compute the depths of this point, so we do the same thing, right? But all the signs will be looking in the same direction. So basically, if we take average of these signs now, the average will be a vector of relatively long lengths, and 1 minus this length of this vector will be then small value, which will say that the depth of the point is small, which it is supposed to be because the point is far from the data. So this depth doesn't satisfy all postulates, so it is continuous, but it's not a fine invariant, it's not monotone on race. On the other hand, it is robust, right? So as we will see, there are still advantages of using these depths too. And yes, this is the picture which I've shown for the previous depths, right? So basically, we had half space depths, projection depths, and spatial depths. Now let's see what else we can have. So we can have more depths actually. These are notions which, this is, say, my personal selection. I don't say that there are some other notions. I don't think they are important or something. It's just me who put these on the slide, right? These ones are being used, and they're actually useful, like Mahalanobis depths, convex half peeling depths, simplicial volume depths, simplicial depths, Zenoid depths, LP depths, expected convex hull depths, geometrical depths, and length depths, or beta skeleton depths is generalization. So now let's look at the properties. I will not be just going to I started with maybe some theoretical introduction of depth. I will not be going much into properties. I will rather be speaking about properties, speaking about applications directly. So let's speak about invariances, right? So let's take a data set, so our data, right, and then apply some transform. We can apply orthogonal transform, right? So basically it's translation, so a shift, then isometric transform, rotation, basically, right? Then we can have additional to translation linear transform, we multiply with some non-singular metrics, and we can have combinatorial transform. Basically a transform where the set of minimal random partitions of our data set remains unchanged. Yeah, so these are the main things, and this is actually interesting exercise. It's actually good that I'm on my laptop because I can now use the magnification. If it will work, yeah, it does. So if you compare for spatial depth these two pictures, it's interesting that it's not necessarily noticeable immediately, but basically they are identical up to a small rotation. The only thing which makes them not to look identical is the difference of the scales of the axis and ordinate, because I just made them have the same size on the plot, on the slides, right? And that makes them kind of different. But if you look more precisely, it's actually literally exactly the same picture, just rotated and shifted, right? These two. So nothing changes because the spatial depth is invariant with respect to translations and isometric transforms, right? So basically, this is this picture just shifted and a bit rotated. On the other hand, when we now try to further modify our data, applying oh no, we have to, sorry. Restart it, then I'm sure that I have good view. If we further try to modify our data, apply linear transforms and combinatorial, actually spatial depths will fail to keep the same shape of the contours. For projection depths, these three will be still more or less identical, while this one will start to differ, and actually half-space depths, which is even combinatorial invariant, will stay the same. And when I say the same, what we can do, we can now shift the clear data and show the depths ordering, where we calculated the depths of each point and just plotted them. And the basic ordering would be the ordering of the clear data, non-transformed one. And what we can see that for spatial depths, well, only orthogonal transform has the same position as the initial data. Then the affine transform and the combinatorial transform change the data. Projection depths will stay affine invariant, but will change the order of the points when we speak about the combinatorial transform, while half-space depths will actually keep the order exactly the same. You see all the four three differently transformed data stay in the same place. Okay, so why affine invariance is important, actually, right? It depends on your task, right? There are tasks where you actually don't need it, right? You can think about machine learning. Many machine learning methodologies don't possess affine invariance. Let's look at the task of search of a multivariate median. So I've created a very simple data set having 14 points, the red points, with one outlier. And you see this outlier is not actually, it's nothing very particular. It's something one can have even working with image data, in sense that it's not that this outlier has very big values, right? Everything is this data between 0 and 1, and the outlier maybe has 1.5 on 3 axis. But it's outlier rather because of accumulation of the high values if we have many coordinates, right? Even if when the range of the data is pretty restricted. So, and then what we see, it is actually very interesting that if we take coordinate-wise median, something which would be the first idea, actually first good idea of robust estimator, as you can see that half-space depth of this point will be equal to 0, right? What does it mean? This means that in this sense, the coordinate-wise median will be laying outside the convex hull of your data, which makes it a bad estimator for location of the data, right? It's even outside the convex hull. The coordinate-wise mean will, of course, be always inside of the data because it's their linear combination. But having the depth 1 divided by 14, which means it will have as small depths as the smallest depths of any sample point, right? So also it would not be really deep in the data. While the rhombus, which was this rhombus, this one, yeah, which represents the Tukey median, actually will be nice inside of the data, and of course we'll have high depths because this is how we computed it. So the next property I wanted to speak about, it doesn't apply to all depths, but in particular to half space it does. It's the asymptotic normality of the estimator, right? I find it's very nicely surprising in the sense that we are doing some geometric combinatorics, right? And then we come up with an estimator which is asymptotically normal. And actually the conditions are not that difficult, so it's not, there is nothing complicated in conditions, so this is just continuity. The depth is positive there, and then it's per point, so this condition can be a bit tricky, but it's per point, so for many points, for infinitely many points, this will be true, right, often. And we will see something like asymptotic normality, so we will actually converge to some distribution which is normal. Yeah, plotted the population depths, distribution to which will converge, and something we have for empirical depths with 320 bivariate observations. Connected with this, let's look at an application, the imputation of missing data. So you see the, and we'll try to do it using the data depth notion. So you see the bivariate data basically here, and then there is, for one observation, having the value is 3 on abscissa, we have ordinate which is missing, okay? So that will be represented as this red line, right? It's here coordinate 3, here it can be any coordinate. So how can we do now imputation, robust imputation of missing data using data depths? Well, it's in similar way as we compute conditional mean when we want to do imputation using conditional mean, right? What we will do, we will fix the coordinates of the observation for which we impute. We will fix the coordinates which we know, and then for coordinates which we don't know, we will be searching for the conditional median, for example, conditional half-space depth median, right? And that's something we will find. And for example, if we have a set of 50 points, so this is the real value of the data generated due to Cauchy distribution, and this is the prediction made by this by the conditional half-space median. And when the size of the sample will be increasing, you see that we actually come closer and closer, and we keep the asymptotic normality. Okay, the asymptotic normality, one should be precise that this will hold only in univariate case. In general, if you look at the distribution, so for distribution of half-space depths, the estimator itself will be asymptotically normal under relative minor conditions, while the distribution of the median, in general case, will not be asymptotically normal, so it will be only in this univariate case. Sorry. So basically, yes. So then, of course, one would need some wrapping procedure, kind of initialize the data, impute them, and run in a loop until we converge to some result. So continuing half-space depths, I also would like to show its interesting, but maybe even like double interesting feature of this data depths. It's that the empirical estimator of the data depths is actually biased. It will take smaller values than the population version we would like to have. So let's do some algebra. So we fix direction. This is the point for which we want to compute depth z, and this is the probability distribution with respect to which we will compute the depth of z, right? So, and let p bar be, well, this basically in projection on u portion of the data which is say further than the projection of z, right? We can, so this is the quantity which given p, z, and u exists, just fixed, and we can estimate it also from the sample, right? If we have instead of x we have n observations, we can estimate it, and the estimator will be unbiased, and it will be just the average of the indicator functions, whether the point of the sample in projection on u is further than a projection of z or not. So now we can actually define using this the finite sample version of the half-space. It's exactly the expression you saw, just written in a different way. The expression you saw when I defined the half-space depths. But then, if you want to see what will be this value on an average, right? We can do the following mathematics. Okay, on an average, I mean, like probabilistically, we will take expectation, right? And then it will be expectation of this expression where we will plug in the estimator, okay? But then it is natural that expectation over the infimum, right? It's like we calculated everywhere infimums and then to the expectation will be smaller actually, right? Then if we'll take first we'll be calculating expectations and only then taking infima, right? And which is fine on its own, but this expression is actually equal to this expression, right? That's how we defined it, and that is the population version of the half-space depths. So basically what we'll have that always the empirical estimator, which we use for half-space depths, will be smaller than the population version. This is something which is phenomenal close to what we call in machine learning overfitting. It's just because we overfit some parameters, and parameters, it's our vector u, to some particular data set, right? And one can easily like sample it for 3 distributions. You see that depending on the size from 10 to 1280, we can see that these are like median and mean, so points are mean and median, these are box plots, right? Values of the empirically calculated depth function. So there are 2 aspects which are interesting. First, it actually gives this nice connection to machine learning because the half-space depths can actually be represented as a sum of point-wise losses, right? But second interesting thing is that usually we don't calculate half-space depths because it has high complexity, so we approximate it, and we approximate it using some algorithms which search the minimum, and since we approximate, we might make a mistake, and so we will not find the best value of the best optimizer. We will have some value which will be probably higher than what we were searching for, but apparently this contributes to the reason why approximation of the half-space depths works actually well in practice, because if we didn't manage to get this value, it's actually not that bad, because while we'll be minimizing, we will stay somewhere here and we'll be closer to the real depths than if we would have found actually the empirical estimator. So one of the properties of the depths is also robustness. So these are robust notions, and they are really robust with respect to outliers. Like in a really, maybe it's one of the most robust statistical machineries. And here what you can see, this is asymptotic breakdown points of medians of different depth notions, right? So you can see that it actually varies depending on what was the initial purpose of definition of these depths, and where we use it, for what do we apply it. Sometimes it's actually 0, right? Like for Mahalanobis, expected conical geometrical simplicial volume of zonoid depths, right? But it also can be a relatively high breakdown value of the median, going up to 1/3 or even up to 1/2 for projection and for spatial depths, the 2 depths which I have represented, right? What can we do with the property of robustness? It actually gives a very nice application, the application of anomaly or outlier detection, right? In statistical world, we would rather say outlier. In machine learning, we would rather say anomaly detection. So what we want to do here, we have some data, which will say some learning data, and then we'll have some new data, or it can be also data already belonging to data set, and we want to say for this data, is this data normal, the green points, is it okay data, or is this data abnormal for my current situation? So how we can do it with data depths? Basically, it is relatively simple. We just calculate the depths, right? So here what you can, so I've just generated some simple example where everything will work because it's synthetic, right? We have 90 normal observations, the blue ones, and then we have 10 abnormal observations, the anomalies, right? The red ones. And we calculate here projection of half-space depths. And we can actually see here how different notions will provide different notions of data depths, give us different values, and which will allow us more or less to detect anomalies or not, right? So basically, if I just what do? I just compute the depth of each of the points, right? And then I plot them in increasing order, right? It's just that when I solve some practical task, I of course don't know, well, first of all, I don't see the data, it's never in dimension 2. I don't know which of the data are anomalies, and what I would see here, I would not see difference between blue dots and red pluses. Everything would be blue dots, for example, right? So I would need to do something. I would need then to find some threshold. And if I'm lucky, I actually would see some threshold. If I'm less lucky, or if it's another depth notion, it would be more difficult. I would need to establish this threshold in one or another way, right? And here we see the difference that the projection in half-space depths would actually, due to their nature, give us different ability to detect anomalies. Similar situation would be also with, say, simplicial volume and simplicial, simplicial volume and simplicial depths. where the simplicial volume depth, which is we will not be really able to detect very well this data, while sorry, we'll be able to in its robust version we'll be able to detect well the anomalies, while the simplicial depth, since it's vanishing immediately outside the convex hull of the data, will not be able to detect anomalous observations, because their depths will be in the same band of depths for some normal observations, so they will be missed. Nevertheless, even such cases, they can be useful in anomaly detection. If we have some noisance in the data, we have additional source of anomalies, right? So what we can have, for example, right, because this looks very, very, very idealistic, right? Often we'll have something worse. We'll have some polluting data here, and we might have some group of anomalies, right? And here we actually will be able to detect anomalies also with projection depths, basically the entire belt of anomalies, so it kind of in this case might even work, providing some reasonable ranking if we choose a good threshold. This projection depth still working. Another interesting, so if you elaborate a bit more on robustness, because if you want to detect anomalies with the data depth notion, actually it is a very robust one. So I've taken a very simple but like relatively honest comparison with the autoencoder, at least from my point of view, where I tried different losses, so L1 and L2 loss, and so what is autoencoder? I just train it on the data, I put data on input and on output the same observation, and I try to learn the structure of the data using some bottleneck, which can be called the code of the data, right? And then the idea of the detection of anomalies would be that I give here observation, I reconstruct it, but I know the observation. So if the reconstructed observation is close to the original observation, it's normal data. If it's very far, then it's an anomaly. Okay, so that's how one can do it. And I did this comparison for autoencoder with the projection depth, but on data which is very heavily contaminated with Cauchy distribution. Okay, in dimensions 10 and 20, we speak about 1,000 total observations. So what do we see here? So this is a portion of anomalies which I increased from 5% to 45%, which is okay, maybe a bit unrealistic. This is the right. So I'm not trying to set up some threshold. I just order points by score. Is it the prediction error of autoencoder, or is it the value of data depth? And then I will put the threshold somewhere so that I detect all anomalies, and I will want to see that how many anomalies. So what is a portion of anomalies in the portion which I told are anomalies, right? So this, I said, okay, this is the last anomaly. I detected for sure all anomalies. Now, what is a portion of anomalies in this chunk, right? So if I'm doing very well, this is what data depth does in most of the cases. It's the blue one. You see, I will be close to 100%, while autoencoder will actually still work for contaminations which are 5 or 10% of contamination. It will work. It's just what this. So the experiment was repeated, I guess, 50 times or 100. What will happen is that autoencoder actually will work, but from time to time you can be very wrong, right? So basically, once you train on autoencoder, it will work. Second time it will work. Third time it will work. But 1 out of say 10, you will train autoencoder, which will completely mess anomalies with normal observations. And if the amount of anomalies in the data increases, well, it becomes more and more difficult for autoencoder to detect them, while even with high contamination, the data depths will actually be still continuing to manage this anomaly detection task. Continuing on the anomaly detection using data depths, one actually can think about some kind of explainability, right? In the sense that if we have a group of anomalies, we actually can not just detect them, we can say more about them. So how does it work? When I will be, just to recap on something which is maybe already clear, when I will be calculating depths of each point, there will be a direction, optimal direction connected to the depths, right? So basically for half space depths, it would be something like this. There will be projectional points, and there will be, this will be the portion of the points which are furthest and the point of interest on this direction, and I will be searching for a direction to minimize this portion, right? And the direction which will minimize this portion, which will minimize the depth, will be my direction of interest, okay? So now what I can do actually, for my sample, I will compute all depths, and for each of the depths, to each of the depths, I will associate a direction on which this depth will be minimized, okay? So now these directions will tell me a lot. First, for an anomaly optimized direction, you can see it like principal components for when we try to maximize variance. Here it will be just that it will show rather which variables mostly contribute to abnormality of a particular observation. Then we can have something like directions plot. So basically what do we have here? It's for each direction projected all points, and in the red I put the point for which this direction is optimal, right? So what we will see that there will be 10 directions for 10 points with their smallest depth values, which will actually be somehow similar to each other, right? So basically they will be on the same distance from the data set, from the data sample, and we see that they will be anomalies kind of, right? Because there is this gap here. So what we can do first, we can still look at the directions themselves. For example, compute the similarity of directions. And this is a matrix of the cosinuses of angles, well, basically, sorry, the scalar product simply between the two directions, right? And what we can see that there will be 10 points here for which the directions are very similar to each other, right? So that will mean actually that for these 10 points, also all directions are similar and distance are similar, and then without seeing the data, right, in some multivariate space, we would see that this is a cluster actually of 10 anomalies somewhere. One should be also cautious because this works in linear manner, right? So if you would like to have some explanation which is non-linear, unless we do extension of the space, this of course would not work. So I would then like go to some generalizations. There are many applications of data depths. There are also implementations if you want to try, both in R and in Python. I say examples because there are others, these implementations in which I participated, but there are also others by other authors. So you have several libraries in Python and maybe around 30, if not 50 R packages which compute data depths. And data depths have been defined for different spaces, right? For Euclidean space, what we have seen today, but also for functional spaces, for directional data, for space of matrix data, for curves, for space of random sets, for space of rankings observations, and on the space of graphs very recently. I will show, so not to this be just words, I will show one application of the data in the space of curves, because it's something we did. In a different way. So basically, but we'll start with some real data. So we speak about now brain imaging data, and for brain imaging we studied the pairs of twins, of all the twins, which would allow biologists to take a look at some diseases and try to understand do they come from genotype or from phenotype, right? So for each individual we had 1,000 fibers in connecting the motor cortex, the part of the brain where we think about our movements, and the brain stem where we distribute these signals to our body. We would like to answer, we can answer several questions like information compression, detection of outliers, registration of curves, and genetic dependency, where we actually will do homogeneity testing using data depths on the space of curves. So this is what the data looks like. So this is these curves which connect motor cortex with brain stem in left and right hemisphere. We take just one part of them. So this is if we compute depths for each of them. So this is information compression because we have so many fibers in the brain that sometimes we want to compress them and represent one pathway with only one fiber to have better understanding. This is outlier detection. So you can see this is some kind of curve box plot where we can see some kind of median observation, then say 50% of more central, 50% of least central, and in red outliers. I'll go faster on curve registration, not to take too much time. So the curve registration, we would like to align all, basically we have many patients who put head in scanner on the different angles. We just want to align all of them. So we do that before treating the data properly. And then what we do homogeneity testing. Basically between these twins, there were twins who are monozygote twins and dizygote twins, right? Monozygote twins, they share actually all genes, and dizygote only around 50%. So what we have run, we've used this to run the homogeneity test whether two distributions are similar or not using the curves, the brain curves of these twins. And this was we ran the Wilcoxon rank sum test on that. And what we can see that basically, and this are also the DD plots where for each point its depth with respect to first and second twin for each of them. So for example, one twin is in red, another twin is in blue, and this will be depth with respect to red twin and with respect to blue twin, right? And we can see that if the twins are dizygote, we actually do see that the two distributions are separated, and when they are monozygote twins, then the distribution overlap a lot, and this is also something we see in the p-values, corresponding p-values of the homogeneity test. Okay, so now a bit about challenges we face with the data. So one of them is computational, because what we see, this is computation times, and with the computational times, what we see is that basically both axes are logarithmic, right? So this means that if we see this line or this line, this means that we actually cannot realistically compute this depth, right? Because this is time which grows exponentially with the dimension and with the amount of data. So if we look at complexities of this, we can have for good depths, good in the sense that they are robust and define invariant, for example, and they nicely reflect the geometry of the data, we would have something like this or something like this, which is pretty high computational complexity if we want to compute these depths exactly. So the question is what to do with this challenge, right? So, right, how we can still apply this nice methodology if we have this computational constraint. And it actually happens. It's not some theoretical result, but can rather be seen as a conjecture that nice depths are difficult to compute. What I say nice, so you see there are like 3 dimensions in this table. There is affine invariance and absence of affine invariance. Then there is heavy to compute, exponential, so the exponential times of something which is like n power d, and polynomial time, n power something constant, right, which doesn't grow with dimension, and the robustness. So robust depth notions are in italics, right? Also about these two, it's not that's just state of the art, right? So they are not robust, but it's just an algorithm which allows to compute them in polynomial time has never been created, right? So maybe it can be. But for the other, for the blue depths here, this convex has half-Pillian, majority, half-space, projection, and simplicial depths. We actually know that these are nice depths, which we cannot compute exactly unless we are ready to pay exponential time complexity. So the idea to approach this would be to use first to select a subset of depths, which we call the depths which satisfy the projection properties, and these are the depths which actually satisfy this equation, this result established in 2004 by Rainer Dickerhoff, which actually says that there are depths for which you can just search for a minimum over all directions, and then on these directions you compute univariate depths, which is easy to compute because this has complexity O of n, right? And then what you do, you just try to minimize, right, over finite number of directions m. You, of course, cannot have it infinitely many. For half-space depths, what it would mean, right, so that multivariate half-space depths can be decomposed in univariate half-space depths, right? Which would be just, in univariate, is just basically the evaluation of the cumulative distribution function, or its empirical version. So yeah, how it works, I give more sense to the picture which I've already shown. So we draw some direction, right? So we want to compute depth of red point with respect to the data. We draw some direction, randomly or not, this is a good question. We project all the data on this direction, and the half-space depth on this direction will be, so univariate half-space depth will be just the portion of points, minimum basically between this and this. So here it's less data, so it will be 16 divided by 50, right? If we take another direction, this will be 13 divided by 50, right? And we'll be searching for direction until we minimize or we think we have minimized. So now, if you want to do this method, right, so clearly this will not be a nice task. It will not be, unless we have some difficult assumptions, it will not be some convex optimization task, right? So we need to do something. So let's first take a look. How do they look, this optimization task? And actually, in some simple cases, they don't look that bad, right? So basically, what we are interested in centers of these blue areas. They're always like symmetric because the depth is symmetric around the center, so it's either left or right, right? So basically, we have to find these blue areas, and you see, it actually can be possible, right? With some kind of method, we just should construct some nice optimization routine, right? So what do? We take as basis this weak projection property, which is satisfied by a number of depths, but from far not by all. And the problem is that okay, we will be developing some statistical computational methodology, but we don't know the exact value. So we actually, and this is empirical, so we actually can't do much. But what is good that what we will be doing will be always minimizing depth. So if we fix everything but the depth minimizing routine, right? We know which of them is best. Even if we don't know how close it to the real depth value, but we know which of them is best, is the one which delivers the smallest value of the depth, because we are always minimizing, right? So now we actually can do a play around. It's just a lot of work, right, to do, and we have to somehow check different methods. Actually, it is possible, right? For example, we use some metric, it's average rank, right? So we run many times method, and we see which of the methods gives the smallest depth values, how many times, right? And then on average rank, if it's close to 1, is good. If it's high, it's bad, right? And we can construct, for example, such a table of like conclusion of our results, where we try different distributions to be relatively agnostic and different methods, and we actually see, interestingly, that for good depths like half space projection or asymmetric projection depths, we can have some nice pictures where dimension 20, for example, we see that Nelder-Mead coordinate descent work relatively good. So this is what happens in one iteration of optimization, right? So basically you see that these two methods are random, so they cannot go far. But here in 1000 directions in dimension 20 with 1000 points from Cauchy distribution, it's actually like very challenging case. With the methods, like the optimization methods, we actually can achieve pretty low depth values after 1000 directions. And it happens fast, because we approximate, we use only 1000 directions. So this is 1000 points, 1000 directions in dimension 5, 10, 15, 20. So let's fix this value. For example, we can compute depths with some precision, believing it's good, in dimension 20 for 1000 points using 1000 direction in 0.03 seconds. If we now put it on GPU architecture, it will be even faster, right? So if you look at the same value, for example, here, right, this is the same value, 0.03 seconds, but here we have used dimension not 20, but 100, so it's 5 times faster. Then data set size would be 10,000, so it's already 50 times faster, and we also will have directions, 20 times more directions, so we're around 1000 times faster, and this we have done with a GPU on a single laptop. So that's actually very fast. So I just would like to conclude with some open questions, which from my point of view are important for the field of data depths. I guess there will be people who would disagree. So first, it's to define some adequate depth notions which reasonably describe the multimodal distributions. There are already examples of how to do it. Like machine learning community finds that it's not enough. Still computational challenge for other depths. So for projection, depths satisfying weak projection properties more or less resolved in some way, but for other depths, we actually still don't know what to do. And on theoretical side, the finite sample properties, something like, for example, concentration inequalities, convergence rates, this is something which still is much open question to many of depths. Why? Because they are non-parametric. Usually they don't assume much about the data, and it makes very difficult to derive such kind of results. I very much thank you for your attention. I will be very happy to answer questions.
Thank you very much, Pavlo, for this nice talk. So now this is questions, so please go ahead.
Hi, thanks for the great talk. I was wondering about the half space depth one, and if there's a reason to generalize it to something like a convex code. You could imagine that it would be harsher on the outliers. Is there a reason to do this? I guess it's the computation.
So what do you mean generalize to convex hull?
Not hull, convex cone.
Convex cone. Okay, sorry. Yes, I apologize. There is perfect reason to do that, absolutely. So, and it actually has been also done. So what I presented is just a snapshot, of course, about data depths. It's a vast literature with thousands of articles. It has been done in Prague by Daniel Glubinka, I think Vinchalik and Kotik. There is a paper on that. So what it does, it defines depths, a more local version. It actually relates to the first problem which I've described. So it relates, it underlines the local features of the data, right? So depths which I presented, they rather capture the global features of the data, and this would rather focus on localities, and maybe would, if you have multimodal distributions or distributions which are non-convexly supported, it would actually give a better idea of what is happening in the data.
Thank you for the nice talk. You mentioned in the beginning that these contours could be also thought of as quantile functions. So do they behave well in that sense? For instance, is the probability content of those contours, does it have good properties, or does it, I'm expecting that if you take the interquantile ranges or whatever lies out of it, does it fulfill the probability content it should have for any of those options?
It's a good question. It's a good question. So so it should be calibrated for probability in the sense that the contours would correspond to quantiles, and for some distributions you can even have the monotone correspondence between the depth function and between the density function, for example, for elliptically symmetric unimodal distributions. On the other hand, this monotone transform should still be found. So if you have depth of the contour is depth, it's something which is defined and calculated in the way which is shown, but it will not necessarily tell you something about the probability content. On the other hand, there is a notion of depth based on optimal transport, where you actually can have something which corresponds exactly to the probability. But this is something which I didn't mention that in presentation. Yes, but the notion of depth, which is based on optimal transport, yes, that would give you something there. You can where you have mapping, for example, to the unit sphere, where you have folded spheres with uniform distributions on the spheres and on the array. Then you can actually speak about probability exactly. Yes, that would correspond to some kind of multivariate quantiles, also with probability. Otherwise, you would need to calibrate.
I thank you for an interesting talk. So depths seem to suffer from this curse of dimensionality, especially computational complexity of depths. So in some problems, we're often able to take advantage of some approximately low-dimensional structure of the data, like the data are close to, say, a low-dimensional subspace. But this seems to sort of contradict with the property of affine equivariance, right? So affine equivariance seems to tell us that, well, if we simply sort of rescale everything to the identity covariance, then we are not taking advantage of this approximate low-dimensional structure. So is there a way to reconciliate these difficulties, and is there a way for the depth to take advantage of the approximate low dimensionality of the data?
Yes. So that's actually, yeah. There are several questions in your question. Yes. So first, I think it's important to mention that speaking about the cures of dimensionality, right? In a statistical way, I would not say it really has cures of dimensionality in sense of convergence rates, right? So the depth has good convergence rates if dimension grows, so actually better than, say, kernel density estimator, right, or nearest neighbors estimators. Speaking about computational, yes, there is computational difficulties with dimension, and that these difficulties, they are present, so that was part of my talk. So I belong to researchers who are trying to resolve at least partially these difficulties. I also would like to confirm, yes, so indeed, for example, the notion I've shown, so to work with brain curves, we have defined a notion of data depths where we had to define the distribution on the curves. And then, so basically you kind of go to some manifold or something similar, and then, so to lower dimensional structure, and then yes, you actually cannot take advantage of affine invariance, and it actually doesn't seem to be useful. So with that I agree. Whether we can, what we can do with depths is on in lower dimensional structures, I would say it's much open question. To my point of view, it's much open question in the literature. For example, how we do rankings on manifolds or something like that. It's an interesting question that could be added to, should be rightfully added to that slide, let's say.
Okay, just a short one.
I would like to react on the comment on the interpretation of depth contours as quantile contours. And an embarrassing fact with depth is that the depth contours do not characterize the underlying distribution, not fully so. And so it's embarrassing to have the concept of quantile that does not characterize the underlying distribution, isn't it?
Yes, yes, that's true. Yeah. There is also this option, yes. It's
And that means that when you are doing depth-based goodness of fit testing, as you have proposed at some point, well, those tests will have some blind spots. Would you have an idea on the nature of those blind spots?
So that's...
Where the distributions are different, but the depth does not capture this difference.
So actually, in the article where we have this curve depths, we actually do we show one example. So I mean, the answer is yes. The blind spots will be where the geometry of the data is not captured, of course, right? So if you can you have to construct two distributions which are different, but the depths would stay the same, right? And so yeah, we give such examples. For example, for that, we give actually in the article an example where we show that here our depths will work. Yes,
that's interesting.
Yes, yes.
And then I have a remark on the spatial depth of spatial quantiles. That you probably have seen that paper by Girard and Schuster on the very bad properties of these contours for higher order quantiles. And I was a big fan of the concept until I saw that. It's really shocking. Would you agree?
With that, yes. For me, what is a bit embarrassing in that notion is the absence of affine invariance, rather. But that stays then a cheap. If you are interested only in medians, so the central one, it's a cheap way to get super robust median, but you have to sacrifice invariance. So it's like, in that sense, it's nice compromise, right?
Okay, and thank you very much with this remark. I propose you to continue the discussion at a coffee break. And we are going to thank again the